Thank you for the introduction and thank you for the invitation. I'm, well, very happy to give this talk and to see many friends and colleagues. I hope, well, in a few months, maybe live and not online. So since, again, don't hesitate to interrupt me and to ask me questions. So I don't see you at the moment, but I can always stop and then see your face and then we can discuss. So indeed, as Roberto said, I would like to tell you about today a problem which is actually is a very interesting problem in material science, but I think is also a very interesting problem in statistical physics and theoretical statistical physics. And I will try to show you that, I mean, what kind of interesting problems in statistical physics is related to. I mean, especially in statistical physics of disorder system. So, well, the problem is how amorphous materials yield under stress. And I will show you that this is, to understand this, we will have to understand and to unveil the existence of a new kind of non-equilibrium phase transition. So the work I'm going to talk about is a series of work done with different people. At the beginning is with Sarojji Nandi and Gilles Terjus, and then actually really the main work on yielding of amorphous material has been done with Misaki Ozawa, who is a postdoc here now at the Ecole Normale Supérieure, and then with Ludovic Berthier, Alberto Rosso, and Gilles Terjus. All right, so let me start now. So what I want to talk about is how amorphous solid deform when you apply a stress. And while there are many different kinds of amorphous solids, as you know, and with very, very different microscopic scale, you can go from, say, molecular glasses or metallic glasses in which the typical scale of the particle is of order of nanometer. And then you can go up in scale. You have colloidal glasses, foams, and granular solids. In granular solids, the size of the particle is of order of millimeters or several millimeters. So while the range and the difference, in the macroscopic difference between these systems is huge, and what I would like to address is how all these systems behave, how they resist and fail when you apply deformation. And in general, so while I have an example here in the bottom of my slide, so what I'm going to study is the typical case in which you have the material, you apply a certain deformation, and you look at what is the stress that is induced, or vice versa, you apply stress and you look what is the deformation that you induce. And so if you do this, the behavior of that you can see are, let's say, they can be divided in roughly in 3 different groups, roughly speaking, and this depends also on the kind of material that you are studying. If you consider models system which are more macroscopic, in which you have sizes, microscopic sizes, which are quite big. So you have the behavior that you see on the left, the one on foams, for example, in which if you look at the stress strain curve, what you see is that when you strain the system, when you deform the system, the stress increase, and then you reach a plateau, and then you start, well, to have some erratic behavior around a certain value. So the system go, we say, from an elastic behavior to a plastic behavior. So it starts to flow beyond a certain value of the strain and beyond a certain value of the stress. So this is the typical ductile behavior or ductile yielding that you have in, for example, foams or granular system. Then in the intermediate, in the middle of this slide, you have the behavior of colloids. So these are, again, experiments. And what you see is that here in the stress strain curve, so in sigma versus gamma, what you see an overshoot. So sigma goes, well, around the maximum, and then it goes down to a plateau value. And the plateau value is, again, it's the value at which you have a certain value of sigma, and then the system is just flowing. So this is a behavior which is a bit different from the one of foams, and this intermediate actually from the behavior that you find in metallic glasses. So in metallic glasses, in which, again, we are going down in microscopic scale. So the microscopic scale for colloids is around to 10 to the minus 6 meter, the typical size of a particle. For metallic glasses, we go down to nanometer. And then there you find a very different behavior. So you find in the stress strain curve, you find that the stress increase. And then at a certain point, you have an abrupt failure in which the stress goes down, and while you have what is called brittle yielding with a sharp stress drop. So you see, you have a quite different behavior, something which goes to something which is smooth for forms, so for large microscopic scale, and then intermediate behavior with an overshoot for colloids, and then an abrupt yielding, which is called a brittle behavior for metallic glasses. So this is, well, all the behavior that you can find in amorphous material. And what I would like to discuss today with you is a way to try to understand this different behavior and to relate this different behavior to the existence of a non-equilibrium phase transition. So more precisely, what I would like to discuss is whether or not there is an yielding transition. So what is an yielding transition is, well, this is something that has been discussed a lot. So let me just give you a kind of definition of yielding, which is taken from a review on rheology by Barnes. Is yielding is the point at which, when the applied stress is increased, the forming solid first begins to show liquid-like behavior. So, well, if you, in this way, it's quite vague, actually. It's not clear how you can define a phase transition in this way. You can always, well, try to define it thinking that if you have a solid, well, if you try to deform the solid, well, you know that the solid, I mean, if you apply a stress, the solid will deform, and then above a certain value of the stress, then the system will start to flow. And so you can ask, what is the value of the yield of the stress at which you have this transition from solid behavior to fluid behavior? This would be the yield stress, and is there a transition related to this behavior? Now, this actually is an interesting question, which is another way to say whether the concept of solid is well defined, let's say, in a statistical physics sense, meaning that I take a system at equilibrium, let's say crystal, I apply a stress, is it going to flow or not? Well, this was actually asked again by the same guy, Barnes, in a review. So the review was the yield stress, a review of Pantarei, or everything flows. So what he was asking indeed was whether one can whether the yield stress exists or not, or whether if you wait long enough, whether or not the system is going to flow. And actually, we answered this question in 2010 with François Sausset and Jorge Kurchan. Actually, if you take a system at finite temperature and in this at equilibrium, for example, a crystal, and you apply a finite stress, so if you wait long enough, the system is going to flow. Then, of course, this long enough can be very large, but I mean, it's not a time that diverge in the thermodynamic limit. So from the point of view of the equilibrium statistical mechanics, well, there is no yield stress, there is no yielding transition. So in reality, of course, there is an yielding transition, and it's an out of equilibrium phenomenon. It's just that the time scale becomes so large that the system has not the time to equilibrate and then to show the behavior that I'm discussing, that we discussed with François Sausset and Jorge Kurchan. So in the following, just to be clear, what the yielding transition is what they are going to consider. I consider a solid at 0 temperature, and then I will deform it, and then I will ask whether or not there is a phase transition when I increase the deformation. So whether the system at a certain value of the deformation will lose stability in an abrupt way, or it's in another way, and whether this can be related to a phase transition. So this will be a phase transition out of equilibrium because the system is prepared at equilibrium at the beginning, but then is at T equals 0, so it doesn't have, we don't let any relaxation take place, and then we deform it, and we look whether or not the system is going to fail, and whether this failure is related to the phase transition. All right, so you can interrupt me and ask me if it's not clear, but this is the thing we are after in the following. So just to tell you what our contribution are, just from the start. So what the problem of yielding, it's a very big problem in material science, and what we are going to do is we are going to restrict on a specific point, which is the existence of this yielding transition. So at 0 temperature, we don't want to focus what happens before the transition or after the transition in the plastic regime. We are only interested in understanding whether there is an yielding transition that separates the, let's say, the solid from the plastic behavior. and how this yielding, whether the property of this yielding transition, whether it depends, if you have, how it changes if you have colloids, if you have metallic glasses, or if you have foams, for example. So what we are going to study is yielding as an out of equilibrium phase transition, meaning that we start from the solid at 0 temperature, and then we do an infinitely slow driving. So we deform the system very, very slow. We always let the system the time to equilibrate, in the sense, find the zero energy configuration after the deformation. And we want to understand whether at a certain point, at a certain value of the deformation, there is a phase transition. And well, our conclusion is that indeed there is a phase transition, and the existence of this phase transition out of equilibrium will allow us to understand the difference in the behavior, in the yielding behavior of the different amorphous materials. So the ones that I just showed you before, metallic glasses, colloids, and foams, for example. All right, so this is, well, the plan. And now, before actually focusing on real model of amorphous material under strain or under stress, I want to do a parenthesis. And I want to try to understand this, try to make an analogy with a well-known problem in statistical physics. So the problem that we have here is the problem of, we have an extended system, which is the amorphous material, and we are going to, let's say, perturb this material and to see whether it's going to fail at a certain point. Now, this reminds a lot the problem of a spinodal transition, right? In which you have a system that is prepared in some equilibrium, then you perturb it with an external field, and then you can follow the minimum, or the system will remain in the same phase until a certain point at which the phase loses stability through a spinodal phase transition. So to make an analogy, what I wanted to focus on now, doing a parenthesis, is to study the problem of the 0 temperature spinodal in presence of disorder. Because this, as you will see, it's going to be really a guideline for us. So it's important to have disorder, because in amorphous solids, clearly there is disorder. And we know that this is an important element. And so what we are going to study now, and what I want to recall you, because it's also an interesting problem per se, is the physics of the spinodal of the random field Ising model at 0 temperature. So what we are going to do is we're going to take the random field Ising model, let's say with all the spins which are minus, for example, and then we are going to change the magnetic field very, very slowly. Each time the system will just go to the minimum energy, and we are going to follow what happens to the configuration, in particular to the magnetization. So the magnetization will start with -1, and then when the field is very, very strong, when H is very, very strong, the magnetization will go to +1. But we want to see whether or not there is a phase transition in between. So the model is defined, just to recall you here, the energy is you have a short-range ferromagnetic interaction between Ising spin, SI, where SI is equal to ±1. And then there is a random field coupled to the spin SI, which is HI, which has a 0 average and the variance R. This R is the strength of the randomness in the random field. And then there is the external magnetic field H. And well, you know that when you look at this problem, you have typically hysteresis, and the control parameter here that you can vary to study what happens to the system are H, the external field, and R, the strength of the disorder. And so this is a problem that has been studied a lot, in particular by the group of Jim Setna, starting from the 90s. And so let me remind you what do you find. So you can do several things. You can do mean field theory, you can do renormalization group. And so, for example, the curve that I'm showing you, even if it's a sketch, is what you find doing the mean field theory. So the main features that you find is, so the first one is that there is a clear difference in behavior depending whether the disorder is strong or is weak. So if the disorder is strong, which is the green curve that you see in the figure on the top right, you find a smooth behavior for the magnetization, which starts from -1 when H is very negative, and then smoothly go to the value +1 when H is very positive. And then, well, when you decrease the disorder, the curve becomes steeper and steeper, and then at a certain point you have a critical point in red at a certain value of the disorder. And if you go below this value RC of the disorder, then the magnetization has a kind of first order or discontinuous behavior, meaning that you follow the negative magnetization until a certain point, and then you jump discontinuously to another point, and then you follow the upper branch of the curve. So, well, this is the very first important feature, and one can understand this feature is that, of course, if the disorder is super strong, then the interaction between the spins is not important, and then you have a smooth curve. But then if the disorder is very small, then, well, you have that let's say the negatively magnetized state at a certain point will destabilize completely, because if one spin flip, then, well, all the neighbors will feel that there is they have a tendency to flip because of the ferromagnetic interaction, and then the neighbor of the neighbor will have the tendency to flip, and so there will be a big jump of the system, which is what you see in the discontinuous blue curve. So this is the first thing. Depending on the disorder, there are two very different behavior, and one is smooth, one is discontinuous, and between the two there is a critical point that has been studied a lot actually by Setna and collaborator. So this critical point is interesting because it's a non-equilibrium critical point, which is is governed by what is called a zero temperature fixed point, which means that the disorder is relevant. The disorder is the most important feature at this critical point. So the temperature is renormalized to 0 at large scale. And one of the key feature of this is that you can compute two different susceptibility, one which is called the connected susceptibility, which is just the derivative of the magnetization with respect to H, average over the disorder. So the overline is the average of the disorder. Or you can compute the fluctuation of the magnetization with respect to the disorder, which is what's called key disorder. And when you have a critical point governed by a zero temperature fixed point at which the disorder is very important, you have typically that the disorder susceptibility is related to the square of the connected susceptibility times a prefactor, which is the effective strength of the disorder at large scale. And this is what you find in all zero temperature critical fixed point. So, well, this is just to tell you that, I mean, there is an interesting critical fixed point that separate the two phases. So these are the first two key features, and there is another one which has been actually found more recently, and which we found actually with Sarojinandi and Gilles Tarjous. So now, if you are in the phase in which you have a discontinuous change of the magnetization, so this is the phase which, in a certain sense, is most interesting to us for the problem of the yielding transition. So this is a phase in which you perturb a state, an extended state, and you perturb it at a certain point. Well, you have a failure of the state, and this state goes to the other one. So it's a little bit similar to what we could think is the yielding transition. Now, we want to understand what is this transition that we have at zero temperature in the case of the random field Ising model. So naively, this is, first it's a spinodal, because, I mean, it's a spinodal. You just follow one state, and then the state becomes unstable. It's a spinodal in presence of disorder. So, spinodal transition at finite temperature in principle do not exist. It's a similar argument to the yielding transition, because, you nucleate the other phase before approaching the critical point related to the spinodal transition. But if you're at zero temperature, you could think that, it exists. And now the spinodal transition, the upper critical dimension for the spinodal transition is 6. You can do a mean field theory. Now, if you put disorder on top of it, again, you can do mean field theory. There is, as you know, for the random field Ising model, in principle, there is perturbative. If you do perturbative RG, there should be dimensional reduction, and so the upper critical dimension should be 8. And so you would expect that the spinodal is critical, and the exponent change below the upper critical dimension, which is 8. So this is, let's say, it's naive, what you find naively using mean field theory and perturbative RG. But these actually are not is not correct. And this, I think, this has been understood really recently, in recent years. So if you try really to do, I mean, if you try to really to do RG, you will realize actually that the perturbative RG is not consistent. And actually what we understood with Sarajinandi and Gilles Tarjus is that the transition, the spinodal transition in presence of disorder becomes a first order transition. So it's not critical, it's like in field theory, and it's a first order transition in any dimension. And what happens, the physics of this transition is related to the fact that you have very rare, well, let me show you actually the movie first. So this is the blue are the minus spin and the red are the plus spin. And this is, well, what happens when you have this spinodal transition and you do a discontinuous jump. So what I'm showing here is really, I'm changing the field very, very slowly. And then, well, I'm just looking at the movie of the three-dimensional random field Ising model, and I'm looking to the behavior of the spins. And so what you have seen, and I do it again, is that it starts from somewhere, a small droplet here, and then this droplet actually just becomes larger and larger. And while this is what we understood, is that this discontinuous jump, what is driving this discontinuous jump is the existence of very rare seeds or droplet of the other phase, which, well, since is a random system, well, you have a certain probability to have this droplet somewhere in the system if the system is large enough. And then this droplet of the other system, what they can do is that they can expand and they can invade all the system. Now, the problem of one can show is that the bigger are the droplet, actually, the easier is for them to expand. But also the bigger are the droplet, the rarer are this droplet. So what we can understand is that, well, the physics is that in the thermodynamic limit, what is going to happen is that this spinodal transition is driven by extremely large droplets, which are super rare, and that and the value at which the spinodal transition, the value of the field at which the spinodal transition takes place, is the value at which the boundary of this droplet is able to depin, so meaning that to push and to expand away. So you should think that this is like a depinning of random manifold, because, well, this interface of the droplet feels a force, because, well, you know that, well, there is an external field, and what the external field is doing on the system is that is favoring energetically the other phase, which means that actually if the interface increase, you gain in energy. Now the problem is that the interface has problem to increase because it's spin by disorder, and this is why it's like depinning. And so while we tested also, while we also had analytical arguments, but we tested this idea in this, using the following trick. So the idea is that the spinodal in presence of disorder is driven by rare effects. And so when you have rare effects, it's super hard to find them doing a numerical simulation. But if you know what these rare effects are, then you can put them by hand, and you can see that they have a drastic effect on the phase transition. So this will validate the fact that, well, they are important for the phase transition. So see, what you have here is the critical value of the magnetic field as a function of the strength of the disorder. And so what we did is that we start, so here this line here is what we call no seed. So this is just we take the system, we just study the hysteresis of the system, of the normal system. And then the other line that you have here are lines in which we put a seed by hand of the other phase. So here, this is the seed is of size 5, here is size 3, here is size 10, and so on and so forth. And so what you see is that the value, the critical value of the magnetic field at which you have the transition for this value of disorder actually decrease the larger is the seed. So it's exactly what I was saying to you. If I have a big seed, well, a big seed will fail before the small seed. And so actually, the phase transition will be due to extremely large seed that are embedded in the other phase. And well, the way to understand, so this curve is going down. This line, which is here, corresponds to the depinning transition of an infinitely large seed. And And then what's going to happen in a real system is that in a very large system of size n, well, the probability to have a seed of the other system is small. It goes in general like exponential minus c L to the d, where L is the size, the linear size of the seed. And so, well, if you want to have at least one seed of size L, you must have that this is of order 1. So this gives you the largest seed that you can have in a system of size n. And then, well, it's known that if you have a seed of size L, just using the critical behavior that you have at the depinning transition, so the critical value at which the seed of size L can depin will be larger than the one that you have for an infinite seed, and will be larger by a factor which is L to the power minus, so L to the exponent, which is -1 divided by nu depinning, where nu is a critical exponent of the depinning transition. So this is just to tell you that if you put these two things together, so you will find that in a system of size n, you can have some seed of some size, but not seeds of any size, because these are too improbable. And this means that actually putting the two together, you will find that the critical value for a given system size will go down. Will go down with n in a logarithmic way, which is log n, because it's due to this very rare effect. And so this is extremely hard to see if you don't put the seed by hand, and if you put the seed by hand, of course, instead you can see it. So here, for example, the green line is no seed. Sorry, the green points are no seed. The green line that you have here is a seed of size 3. And since the two are together, this means that for the size that we used, we had seed of size 3 inside the system. Instead, well, when we put the seed of size 5, we find this value of HC, which is lower, which means that given the system size that we used in simulation, well, we didn't have on this system size seeds of size 5. So the other interesting thing that you find in this curve is that you can really see the existence of the critical point. So we know that if R, the strength of the disorder, is small enough, then the hysteresis or the yielding behavior is discontinuous. Sorry, not the yielding. The hysteresis is discontinuous. And but then at a certain point it becomes a smooth. If R increases, it becomes has a smooth behavior, and it goes to a critical point. And this, you can really see it here, because the effect of the seed disappear at the value of R, which really coincide with the value of RC that we know for the random field Ising model. All right, so while this is all the things I wanted to tell you on the random field Ising model, on the spinodal of the random field Ising model, which is, I think, is the best case, that is the case that we understand well in statistical physics, in which an extended system, an extended disorder system, fail when it's perturbed away from its equilibrium position at 0 temperature. Now, I would like to go to the problem that I discussed at the beginning, which is what happens actually when you try to perturb an amorphous material out from its equilibrium position at 0 temperature by deforming the system. So maybe it's a good time to take question on the random field Ising model, if there are. Otherwise, I go on. No question? All right. So, okay, so let's now switch gears and study the yielding of amorphous material, but I will try to make a connection with the random field Ising model. So the way that we use to study, I'm looking for the arrow, but okay, no, okay. Well, so the way that we use to study to study amorphous material when we impose a deformation is through elastoplastic model. So elastoplastic model are models which are extremely popular in the for people doing theory of rheology of amorphous material, and they are a little bit intermediate between let's say numerical simulation or molecular dynamic simulation and very, let's say, and very schematic representation. So yeah, they're a kind of mesoscopic description of the rheological properties of amorphous material. And so let me describe what they are. So what the idea is that you consider the system, and you divide this, your amorphous material, and you divide it in, let's say, mesoscopic block. And you think that in each mesoscopic block, you can define a local value of the stress. And then, well, when you impose the deformations and when you deform the system, all these local blocks change the local value of the stress. And then if the stress goes above a certain value, which I call sigma threshold, sigma TH, then, well, the system fail locally. So the stress sigma I will go down of a certain amount. And the stress, I mean, the loss of the stress is redistributed among all the neighbors. And is redistributed using the kernel, which is called GIJ, which tells you really, well, it's what is called the Eshelby interaction, and is telling you if locally I deform, how much this local deformation or local change of stress is transmitted far away. So you can work this out using elasticity theory. And so, for example, in 2 dimension has this quadrupolar form, which is cosine of 4 theta ij. Theta ij is the angle that you can define in 2 dimension between I and j, and then divided by rij to the d, and well, in this case is equal to. And then, well, what we want to study different amorphous material. So what changed between different amorphous material is the degree of annealing. This is what we think is our idea. So the different behavior between foams, colloids, and metallic glasses is actually due to the fact that metallic glasses have a very small amount of disorder, are much more annealed, and instead foams, for example, are much less annealed. Well, there is a reason for this, is that if you consider system like foams, they have the microscopic length is much larger, and the microscopic time scale is much larger. Or if you think to granular material even, I mean, the size of a grain is several millimeters, and the time scale actually is almost like seconds. So this means that if you want to equilibrate the system on experimental time scale, given that the experimental time scale are always the same, a few hours, so the few hours correspond to a certain number of microscopic time scale, and this certain number is very different if you consider foams, colloids, or metallic glasses. So in metallic glasses, the microscopic time scale is picosecond. So of course, if you have 1 hour at your disposal, it means that you can equilibrate the system on time scale, which are of order of 10 to the 14 microscopic times. So this means that when you prepare a glass, a metallic glass, and then you study its rheology, when you prepare it, you are able to equilibrate the system on time scale which are much, much larger than the one on colloids, which are much, much larger than the one on foams and granular system. So since you are able to equilibrate on time scale which are much larger, it means that you have annealed the system much better. And in principle, we expect that this means that the system is locally much less disorder. And instead, if you just do it very super quickly, well, if you just equilibrate super quickly, so you change then the system will be very disorder, and well, so the local configuration will not optimize well either the steric constraint or the energetic constraint. All right, so in this model, what we are going to do in order to put the degree of disorder, which is related to the degree of annealing, is we are going to decide that the initial distribution of the sigma I can be a peak distribution, or it can be a broad distribution. So if it's a broad distribution, it means that all the sigma I in my system are very different, which this correspond to a system that has not been annealed well, and the system that has been annealed well has all the sigma I which are close one to the other. And so this is the model. So now what we want to do is we start from an initial condition with a certain distribution of the initial sigma I. We change delta gamma, so all the sigma I are going to change, and then there is one will go up the threshold, and then we will relax locally, and we redistribute the stress on all the others, and then, well, you can have in this way a cascade, an avalanche of change of the sigma. And this reminds a lot, actually, what happens in the hysteresis of the random field Ising model, because in the random field Ising model, what you do is that you have all the spins, they start from, let's say, down, because the initial value of H is negative, And then when you increase the value of H, well, there is maybe one spin that has a local random field which is positive, and so it will be the first to flip. And when this flip, actually because of the interaction with the other, there will be other that flip. So you have really something which is similar to the random field Ising model. At the same time, there are important differences. I mean, the most important difference is that in the random field Ising model, once one spin flips, you have an interaction which is short range and is ferromagnetic with all the neighbors. Here you see that the you have a plastic event at a certain site I, sigma I goes down, and then the stress is redistributed, but it's redistributed using this kernel, using this interaction Gij, which is anisotropic because there is cosine of 4 theta, and then it's also quite long range because there is this 1 over r to the d. All right, so there are similarities but difference, and so while the idea is that we have to study this model to try to understand whether or not there is a relationship with what we have seen in the random field Ising model. So what we did is to actually to study within mean field theory the elastoplastic model and try to see whether or not within mean field theory we find a physics which is similar to the one of the random field Ising model. And the answer is yes. So what we did is to replace. We studied this model like it's like a cellular automaton, and but we replaced the Gij in 2 dimensions. That would be in 2 dimensions with the cosine of 4 theta divided by r to the d, r square actually. We replaced by 1 over m. So it's a mean field version. And then if we do this, we can solve the model exactly. And when we can compute, the stress versus strain curve. And what we see, and we can compute the stress versus strain curve, changing the initial disorder, so the disorder of the system. I remind you that the disorder is the distribution, the initial distribution of the sigma, whether they are all similar or whether they have a lot of fluctuation. And again, this is related to the degree of annealing of the amorphous material. So what we see in the stress versus strain curve, sigma versus gamma, is you see that we have a behavior with a discontinuous jump in which sigma increase and then has a jump and then it goes to a kind of plastic behavior. This is what happens when the degree of disorder is small. And so we call delta sigma the height of the jump. And so you can see in the right curve, the delta sigma as a function of A. A is the broadness of the initial distribution. So you can see that the delta sigma goes to 0 at a certain value of A. And indeed, the transition goes from being discontinuous in the stress versus strain curve to a critical point. You can see the critical point, the sigma versus gamma curve is the blue line, is the dot in the blue line. And then you have an overshoot, and then you have really a smooth behavior for a very small value of A. So, I mean, this is good in the sense that first, we really find the same features that I discussed before for the random field Ising model. Depending on the value of the disorder, we have 2 different ways in which the system responds. If the disorder is strong, the system responds in a smooth way. And if the disorder is small, the system responds through a real phase transition, which is discontinuous. And one can really do almost a mapping between the 2 systems, meaning that what is the magnetization in the random field Ising model would be the average stress, is the order parameter. What would be the field, the external field in the random field Ising model would be the strain, is the control parameter, which the one that we change. And then what would be the disorder is the broadness of the initial distribution. And so, the mean field theory is really the same in the sense that even if you study what are the critical, for example, the critical exponent within mean field theory, the critical point that separate the 2 phases, let's say the continuous behavior from the discontinuous behavior, these are the same. And also other having the same exponent within mean field theory is not so, it's not so constraining, but you can study also other quantities, and really you find exactly the same physics that in the mean field version of the hysteresis of the random field Ising model. So this is, I think, is the first interesting result on this problem. Of course, we did a big approximation doing mean field theory, I mean, we did, I would say, two big approximations. The first one is to say that the system is mean field, so meaning that we take an interaction from everybody to everybody else. And then the other is that the interaction is not, it's at the beginning, so it's anisotropic. So it means that sometimes it's positive, sometimes it's negative. Instead, the one that we consider is just a positive mean field interaction. Gij goes like 1/n. Now, the interesting news is that you can try actually to do a more refined mean field interaction in which you still have something which is long range, but which can change sign. This is what has been done by the group of Mathieu Viard. And you can still, and they still found the same property of the yielding transition, which again is the same of the mean field, the random field Ising model. And then the other interesting news is that you can also simulate the model in 2 dimensions, and you can try to see whether in the simulation you can find a phase in which at low disorder, an abrupt change in the sigma versus gamma curve, and instead in the very disorder, when the disorder is strong, whether the behavior is smooth. And the answer is yes, is what they found in this paper by Mathieu Viard. So this means that, at least from this study, it seems that this analogy with the random field Ising model seems to be good. And it really seems that the way in which a system yield, an amorphous system yield, is different depending on the degree of disorder. And there are really 2 phases, and these 2 phases are separated by a critical point. So while this is mean field theory and the other are simulation, and all this is for a, let's say, an elastoplastic model, so it's not the real system. But now that we have positive results, it's good to go to real simulation and see whether the effect is there or not in real simulation. Now, in real simulation, the difficulty is that it's very difficult actually to prepare a system, an amorphous system, which is very well annealed. And the reason is that, well, to be very well annealed, you have to equilibrate on a very large time scale. And this is what makes actually the problem very difficult. Now, there have been a breakthrough in recent years on the ability to prepare a very well annealed amorphous system. And this has been done in the group of Ludovic Berthier, who actually used an algorithm which is called the swap algorithm that was invented before. But then he found system instead of changing the algorithm, what he did, he changed the system. So he found a continuously polydispersed system in which this algorithm is extremely effective. And so this way he was able to create, to equilibrate system to a value of the temperature, which is extremely small. I mean, it's comparable to the one that you have in experiments, actually even lower. So in this way, actually, this is what you see. I'm sorry that I'm not able actually to use the arrow to indicate, but in the figure that you have, so you have the green line, which is the behavior of the energy as a function of temperature in equilibrium. And then, well, depending on the, what you can do is that you can equilibrate the system on many different points. So even below what is called TG, which would be the experimental glass transition temperature. And from that point, then you do a quench at 0 temperature to get the solid state. So it's, if you start from a point which is called to what we call T onset, and then you quench the system to T equals 0, then you get a system which is not very well annealed, and that we think is very disordered. Instead, if you follow the equilibrium line, you arrive, let's say, at TG, and then you do the quench at 0 temperature, then you construct a system which is very well annealed, and that we think has a low degree of disorder. And well, this is what I think is really the breakthrough that allow us to study this idea, this theoretical idea that I discussed before for the yielding transition. So also the system size that has been used to study this has been, well, quite huge system size, from 1,500 particles to almost 100,000 particles, and then a very large number of samples. So let me now tell you what we find. So what we find, so what we are after are this property that I discussed before in the elastoplastic model that we found, the existence of these 2 phases depending on the degree of disorder. I mean, these 2 different ways of yielding depending on the degree of disorder and separated by a critical point. So while this is the behavior that we find. So here you have sigma as a function of gamma. And here, the different curves correspond to different value. T init is the temperature at which the system has been annealed before doing the quench at 0 temperature. So in this case, you see it's an extremely small temperature. So this is a super well annealed system. And the black line instead here is not a very well annealed system. And what you see is that here, the sigma versus gamma, you really find, well, for the not well annealed system, you find a curve which is this. I mean, all these different curves correspond to different sample. So you have fluctuation, but you find something which is, let's say, rather, I mean, it has no overshoot, no discontinuous behavior besides the small fluctuation that will disappear in the thermodynamic limit anyway. And instead, well, when the system is very well annealed, you find that the sigma increase, but then has a very discontinuous jump, and then you have the plastic behavior. So it really looks like there is a transition between a regime which correspond to systems which are not well annealed, which the yielding, there is no real yielding, it's a smooth change from elastic to plastic behavior, to a regime in which there is a phase transition between the two, which is discontinuous. I mean, there is a phase transition between the two regimes. This phase transition is discontinuous. So this is what is called brittle behavior. This is what is called ductile behavior. Now, the interesting, so, well, this is also, of course, I mean, these are the fluctuation. We can also do finite size studies. So here is the finite size at the lowest temperature, T init, 0.062, where you should expect to have a first order discontinuous transition. And this is what you find. If you average and you can decrease at the value of n, you see that you go over a transition which is more and more abrupt, exactly what you expect for this continuous transition. Now, it's also interesting to see that these two different way of yielding, so smooth versus discontinuous, corresponds in real space to two very different phenomena. So here is what you find if in the case of the ductile behavior. So this is this line here. When the system is not very well annealed, so here what I'm showing is the non-affine displacement, is the part, I mean, of relaxation. Let's think that is correspond to plastic behavior. And see, you see that the system is, well, relaxing in a more or less uniform way. So it's not really, it's not an abrupt failure. And instead here, when the system is brittle, so which correspond actually to this, so this is what you're seeing is how the system behave in this case. So what you see, nothing happens, so there is no plastic behavior. And then at a certain point, bang, there is a shear band that is in the middle of the system, at least in this sample, and which correspond really to, well, to this discontinuous jump that you see here. So you really see that the two different behavior that we see in a certain sense in a macroscopic way in the stress versus strain curve correspond to two extremely different microscopic way of failure. This we will call ductile, and this we call brittle. So, well, this is the first indication that indeed there are two different ways of yielding. And now what I'm going to look at is whether there is a critical point that is between the two. I mean, whether that is separating the two. And so what you see on the left, so let me just check how I'm going on time. Okay, so what you see in the left is the sides of the discontinuous jump as a function of temperature, and so what you see here is that the delta sigma as a function of well, this is for different system size. Delta sigma as a function of temperature. You see that you go from one regime in which delta sigma is different from 0 to a regime in which delta sigma is 0. Well, this is exactly the same thing that I was showing before. Now, the interesting thing is, if you look on the right, these are the fluctuation of the delta sigma max, the statistic of the largest stress drops. And so what you see here is that the statistics of this largest stress drop is not critical if you are below a certain temperature, meaning that you find something that does not diverge with n if you do different system size. Below a certain temperature, it does not diverge with n if it's above a certain temperature, but at a certain critical temperature, which corresponds to T init, then we find that this susceptibility increases with n. And this susceptibility is nothing else than what I called before for the random field Ising model key disorder. Is the fluctuation of the order parameter due to the disorder. And this fluctuation actually diverge at the critical point, where the critical point is actually the point at which you go from, I mean, delta sigma goes to 0, so you go from this discontinuous behavior to the continuous behavior. Oops, sorry. Oh. All right, and we also can compare this discontinuous susceptibility to the what is called the connected susceptibility. And again, we find something which is very similar to what you find in the random field Ising model, is that the disconnected one, which is the fluctuation due to the disorder of the order parameter, are actually close to the scale, like the square of the connected susceptibility, which seems to say that this critical point that separates these two different ways of yielding is also a critical point which is very similar to the one that you find in the random field Ising model, and that it should be related to zero temperature fixed point. All right, so this is what we find in simulation, which really tells you that seems to go well with first the mean field result of the elastoplastic model, and also with the result on the random field Ising model. Then we repeat this was done in 3 dimensions, and then recently we repeat this in 2 dimensions, and in 2 dimensions we find very similar results, except that the finite size effects are stronger, but it looks like that the transition is still there in 2 dimensions, which would mean that the lower critical dimension is less than 2. Well, if you can trust the simulation, this is probably due to the fact that the interactions are long range compared to the one that you have in the random field Ising model, which are short range. All right, so this is, if you remember what I told you about the random field Ising model, there are different features of the spinodal of the random field Ising model. There is the fact that there are 2 different phases. There is a critical point, and then there is something which is interesting, which is the physics related to the discontinuous yielding, so the yielding that you see here. And in the case of the random field Ising model, the physics was related to the existence of rare seed from which actually the failures start. And what we see here is that when you have this discontinuous jump, well, you have something here, if you remember, is that you see that this discontinuous jump is related to the existence of what we call a shear band. So a failure which is localized in, let's say, 3 dimensions, is on a 2-dimensional part of the system. In 2 dimensions will be on a line. Now, what we are doing right now is that we are showing that actually this shear band, the existence of this shear band in the case of brittle behavior is very, very similar to this rare seed that we discussed in the case of the random field Ising model. So what you have here on the left, it's a kind of movie of, let's say, the life of a shear band, or the origin of a shear band. So instead that before, in the movie that I showed you before, it was too fast. Now what you're seeing is that actually a shear band starts from a seed, and then when the time increased, actually the shear band start to propagate from the seed, and then becomes larger and larger, and then it invades the whole system. And once it has invaded the whole system, then it's easy actually, well, if I'm trying to deform the system, it's easier for the system to deform because it contains a shear band in the middle, in which the deformation is easier. And the physics of this relaxation through shear band is very similar, really, to the one of the expansion of seed in the random field Ising model, in the sense that what you have to think is that now you have a system which is extremely well annealed, so very low disorder, and then you start to deform. Well, since the system is very big, somewhere with a very small probability, you have some region actually which is not so well annealed and which is more prone to failure than all the rest. And this region, which is more prone to failure, is where the failure will start. And now it will start from here. So we know that if I start to relax, so if I fail here, well, I'm gaining energy because I'm releasing stress. But then once I fail here, well, if I want to propagate this failure, well, there is something that is blocking. And the thing which is blocking is that in principle, the material is disordered. So, I mean, even if it's energetically its power to fail more and more, the system will not do it because, well, you have a kind of pinning of this shear band. Now, the difference, of course, with respect to the random field Ising model, in the random field Ising model, the seed were something which was circular and was expanding like a sphere. Here, what you have is you have an expansion along, well, a shear band. But this actually can be understood, and I don't have time really to go into the detail, but you can ask me if you want, using the anisotropic property of the elastic kernel. You can understand that the better way to have a seed that propagate, so that such that if I relax here, then this relaxation or this deformation, this failure, will induce a failure here at the boundary, which will induce a failure at the boundary, and so on and so forth, is really this geometry with a shear band. And so what we have to study to understand this problem now, it's a kind of depinning transition. So the yielding, the brittle yielding, the discontinuous yielding, is related to a depinning transition of rare seed, while these rare seed actually are these, let's say, low-dimensional objects, so shear band, or in 3-dimensional shear line in 1 dimension. And well, we can also do exactly what we did in the random field Ising model to make more concrete this idea. What we can do in the random field Ising model, if you remember, what we said is that, well, if the transition is due to the rare seed, well, it means that there are super big finite size effects. So the way to see that these seeds are really relevant is that even if the system is not very big, you can put them by hand. So you can put one seed that, well, you will need a super big system to have, but you put it by hand, and then you see how the seed, the existence of the seed, affect the transition, and in particular whether the value of the critical value of the deformation change. And so this is the figure that you have on the left. So here you have the value. So when I deform in the system, gamma y is the value at which you have the discontinuous failure of the system. And what you see is that the black curve corresponds to no seed. Then if I put a seed which is the diameter, so it's an ellipse, it says a diameter of 16, you have almost no change, which means, like in the random field Ising model, which probably, given the system size that we are considering, seed of size 16 are typically inside the system. But then if we put a seed which is larger, of 32, then we see that actually the system failed before. It's the value of gamma y is smaller. And if you put a even bigger seed of size 50, then the system failed even before. So this is very, very similar to what we found in the random field Ising model. And then we can think what is the value, the real value in the thermodynamic limit at which the system would fail. Well, this could correspond to the value of gamma y at which I have a very, very extremely large seed of, so in 2 dimensions will be a line, and I'm asking what is the value of gamma, which this line can actually depin and propagate to infinity. And so this, well, is, and the fact that what you see in the figure, well, it's a way to show this. And there is another interesting point in the figure on the left, is that exactly like in the case of the random field Ising model, you see that the effect of putting a seed on the phase transition decrease the more the system is disordered. So the more is disordered, which means the higher is the temperature at which I prepare the system. You see the effect with it decrease, and then at a certain point, which is this dot, which is when T init is equal to Tc. Tc is the temperature which corresponds to the critical point separating the brittle yielding from ductile yielding. Then the effect of putting a seed just disappears. So, well, this is very similar to the random field, and really tells you that in the case of brittle yielding, what is really important is are these rare seed, and these rare seed are related to the shear band behavior. Now, it's nice that you can find also evidence of this in experiments. So what I'm showing in the figure in the bottom right are experiments on metallic glasses, which have been done either in bulk glasses or actually in glass on size of, hundreds of nanometers. So when you go from hundreds of nanometers to a bulk value, it's the same effect. So when the system is hundreds of nanometers small, so the system is small. So it means that in principle, well, you cannot have big seed inside the system. And instead, when you have a very big system, you can have big seed inside. So you expect to see a very different value of gamma y in very small system compared to very large system. And while the figure actually, well, I will not discuss in detail the figure here, but it's really what has been found in the experiments on metallic glasses. So very small system actually have a value of gamma y, which is much larger than larger system, and was exactly interpreted in this way, in this experiment, meaning that in the for very large system, which correspond to the red line here in the experiments, you have heterogeneous, what they call nucleation. It's not standard nucleation, but there is some region inside the system from which the shear band can form, which correspond to the rare seed that I just discussed. So I will now conclude. So what I wanted to tell you is that so the way in which amorphous materials fail when they are deformed seems to be very different. So it seems that foams and colloids, so foams fade in a very smooth way. Colloid have an overshoot in the sigma versus gamma curve, and instead metallic glasses and oxide glasses fade very abruptly. But in reality, we can understand and rationalize all this different behavior, thinking that foams, colloidal glasses, or gamma material are systems which are we have a very low degree of annealing, just because the relaxation times in microscopic, when compared to the macroscopic timescale, are very small, and instead metallic glasses are much more annealed. And so metallic glasses are more annealed, so low disorder, and so we expect to see a brittle behavior, a discontinuous behavior, and indeed foam and colloidal glasses are high disorder, and so we expect a ductile behavior, and we expect a critical point between the two. Now, all the things that I told you about are, let's say, a part of the story. I don't think we have a complete picture, in the sense that I think the Random Field Ising Model was a very important guide to understand what's going on. And also our study on the elastoplastic model also was an important guide. At the same time, I mean, this critical point between brittle and ductile seems to have very strong similarities with the one of the out of equilibrium phase transition in the Random Field Ising Model, but I don't think it's the same. And one thing that we want to do in the following is to study a Random Field Ising Model with anisotropic long-range interaction, exactly like the one that one has with the HLB kernel, and to see whether the property, whether one finds the critical points with different property compared to the ferromagnetic case. And so this would be a way to really study in detail, theoretically, this critical point between ductile and brittle behavior. And then there is the other thing, which is, I think, is very interesting, is in the case of the brittle behavior, I try to argue from simulation and theory, is that this brittle behavior is due to the fact that somewhere in the system there is a region which is far more prone to fail, and from this region is the seed for the shear band. Now, understanding, I mean, when the depinning of this seed and the creation of the shear band, I think it's an interesting depinning transition, but it's a depinning transition of a new kind. In general, depinning transition has been studied in which you have in case in which you have an interface that moves in a disordered system. Here you have something which is different. For example, in 2 dimensions, you have a line, and you want to understand whether this line can actually propagate in the disorder in presence of anisotropic and long-range interaction, which is something that has not been understood until now. So I think that's all I wanted to tell you. So I think there is still work to do. It's an interesting material science problem, which actually is related to very interesting also statistical physics theoretical problem. So thank you for your attention. And now I hope I can see you again.
Thank you, Giulio.
Okay, thank you, Giulio, for the very interesting talk. We have some time for questions, if there are any. So, any questions? Okay, I see that Roberto Livi has a question.
Do you hear me?
Yes.
Yeah. Okay.
Yes.
I was very. First of all, thank you very much for a very nice seminar. It was really interesting and illuminating for the kind of problems you're discussing about. I was very curious about your last comment on the idea of how to say, elaborating more the model, introducing explicitly not a mean field representation, but a true long-range interaction. And I guess that you were referring to the idea that probably this could modify significantly some features, in particular criticality and out of criticality behavior of the model. Am I correct in this sense? But I think it's a very big effort to go in that direction. I mean, it might be a very challenging theoretical problem.
Yes, I mean that's precisely the idea. Yeah, I agree that it's not easy. I think it's more than the long range. It's not much the long range part, which is the problem. Is really the anisotropic interaction. So the fact that interaction can be positive and negative, and also it's not positive or negative at random, but it's positive or negative with this quadrupolar. So for example, this is really the key, which makes that the seed are shear band, so are, let's say, low dimensional object compared to the random field Ising model where there are spherical droplets. So this is something that we understand, at least. Now, for the property of the critical point, I agree with you. In principle, it's hard. So the first thing we are going to do, and we are doing right now, actually, with together, well, with Gilles Tarjous, Mizaki Ozawa, but also Francesco Zamponi and Saverio Rossi, is to study already in the elastoplastic model with this anisotropic and long-range interaction to study numerically the property of the critical points, because in that case we can do very good numerical simulation, and so try to study it well and to try to understand how much is different from, let's say, the short-range ferromagnetic case. And then, yes, and then we would like to do the theory, which I agree with you that it's something difficult, but okay, we are.
Yeah, it's our job.
Yeah.
It is our job to face with difficult things, but on the other hand, maybe could one figure out that there will be a sort of intermediate step rather than going directly to a long-range interactive model to find out a sort of, how to say, effective model for this special kind of depinning transition you have been describing up to now. So maybe one could figure out a sort of a simplified but a bit improved model in that direction.
Yes, I think it's, again, I think it's the problem is mainly, is not much, again, the long range is really this quadrupolar effect. So I agree with something we're thinking about, but it's so for example, I can tell you one thing we thought about, but which is not correct, but okay, it's still an idea. So when you have the shear band and you have the propagation of the shear band, so what is clear if you use the quadrupolar interaction is that if you have a shear band like this is the best configuration to keep things going. So it's the best thing that can propagate. So from this we understand the, because from the quadrupolar interaction, this each time that there is something that fails at the boundary, then all the things actually add up at the tip of the shear band. Now to understand depinning, the fact is that when this is increasing, it can reach a region in which you have a very, disordered fluctuation which pin the system. And so at this point, actually, the shear band, what it has to do, it has to move up or down and then try to go again. And this is something that I don't know exactly how to model this. So we thought maybe we can use directed percolation for this. Well, in directed percolation, I'm just looking whether this can directly percolate until the boundary of the system. But if we do this, at least the exponent that we get are not good compared to simulation. So clearly there is something which is not correct. But this is the kind of thing we are trying to do now. So using a little bit the result from simulation to try to cook up some intermediate model, as you were saying.
Very nice. Thank you.
Thank you.
Let me show you just to say hello and thank you very much. It's really a great pleasure.
Okay, any other questions? Okay, so since there are no more questions, I think we can thank again Giulio for the very interesting talk. Thank you. Thank again Giulio for the very. Thank you.
Thank you, Giulio. Have a nice time.
Thank you.
Thank you, Giulio. Have a nice time.
Thank you. Bye.
Bye. Thank you.
Ciao a tutti.
Ciao.
Ciao.
Ciao. Ciao a tutti. State bene, mi raccomando, sai Covid.